Combinatorial auctions. In combinatorial auctions, a large number of items are auctioned concurrently, and the bidders are allowed to express preferences on bundles of items. This is preferable to selling each item separately. When there are dependencies between the different items, this problem has direct applications, may be viewed as a general abstraction of complex resource allocation, and is the paradigmatic problem on the interface of economics and computer science. We give a brief survey of this field, concentrating on theoretical treatment. Introduction. A large part of computer science as well as a large part of economics may be viewed as addressing the allocation problem. How should we allocate resources among the different possible uses of these resources? An auction of a single item may be viewed as a simple abstraction of this question. We have a single indivisible resource, and two or more players desire using it. Who should get it? Being such a simple and general abstraction explains the pivotal role of simple auctions in mechanism design theory. From a similar point of view, combinatorial auctions abstract the issue. This issue, when multiple resources are involved, how do I allocate a collection of interrelated resources? In general, the interrelations of the different resources may be combinatorially complex, and thus handling them requires effective handling of this complexity. It should thus come as no surprise that the field of combinatorial auctions, the subject of this chapter, is gaining a central place in the interface between computer science and economics. Problem statement. The combinatorial auction setting is formalized as follows. There is a set of n indivisible items that are concurrently auctioned among n bidders. For the rest of this chapter, we will use n and m in this way. The combinatorial character of the auction comes from the fact that bidders have preferences regarding subsets, bundles of items. Formally, every bidder I has a valuation function Vi that describes his preferences in monetary terms. Definition 11.1. The valuation fee is a real valued function that for each subset S of items, V of S is the value that bidder I obtains if he receives this bundle of items. A valuation must have free disposal, i.e. be monotone. For S, which is a subset equals to T, we have that V of S is less than or equals to V of T, and it should be normalized. That is, V of the empty set should be equals to 0. The whole point of defining a valuation function is that the value of a bundle of items need not be equal to the sum of the values of the items in it. Specifically for sets S and T, S intersect T is equals to the empty set. We say that S and T are complements to each other in V if V of S union T is greater than V of S plus V of T. And we say that S and T are substitutes if V of S union T is less than V of S plus V of T. Note that implicit in this definition are two assumptions about bidder preferences. First, we assume that they are quasi-linear in the money, i.e., if bidder I wins bundle S and pays a price of P for it, then his utility is Vi of S minus P. Second, We assume that there are no externalities, i.e. a bidder only cares about the item that he receives and not about how the other items are allocated among the other bidders. Definition 11.2. An allocation of the items among the bidders is S1, S2, S3 until Sn, where Si intersect Sj is equals to empty set. For every I not equal to j, the social welfare obtained by an allocation is the summations of bi of Si summing for all index I. A socially efficient allocation among bidders with valuations v1, v2, v3 until vn is an allocation with the maximum social welfare among all allocations. In our usual setting, the valuation function vi of bidder I is private information, unknown to the auctioneer or to the other bidders. Our usual goal will be to design a mechanism that will find the socially efficient allocation. What we really desire is a mechanism where this is found in equilibrium, but we will also consider the partial goal of just finding the optimal allocation, regardless of a strategic behavior of the bidders. One may certainly also attempt designing combinatorial auctions that maximize the auctioneer's revenue, but much less is known about this goal. There are multiple difficulties that we need to address. Computational complexity. The allocation problem is computationally hard and complete, even for simple special cases. How do we handle this? Representation and communication. The valuation functions are exponential size objects since they specify a value for each bundle. How can we even represent them? How do we transfer enough information to the auctioneer so that a reasonable allocation can be found? Strategies. How can we analyze the strategic behavior of the bidders? Can we design for such strategic behavior? The combination of these difficulties and the subtle interplay between them is what gives this problem its generic flavor, in some sense encompassing many of the issues found in algorithmic mechanism design in general.